Welcome to the video on titrations. This is Introduction to Titrations. We're going to spend the rest of this unit talking about titrations, so let's get you started. First of all, definition of a titration. That's when you add an acid to a base, or vice versa, you add the base to the acid, and your goal is to calculate the molarity of whatever it is you start with your flask. So you know you have that burette, then burette is often full of the base, and you have acid in the flask, and then you drop it in, and stirring until it turns pink, etc., etc. That's a titration. And the goal at the end there is to calculate the molarity of whatever was in that flask. You know the molarity of what's in the burette. Okay, you are going to get a curve if you try to measure the pH as you add base. Let's say we're adding base to an acid, which is one of the most standard kind. And so if you're adding base to the acid, then the pH will increase, but it will not increase at a steady rate. It will stay low and then shoot up really quickly and then stay high. What we need to do in class is we need to calculate the pH of the solution at any point during the titration. Now this, we're going to start talking about a strong acid versus a strong base. There are 4 positions on this titration curve. The first position, position 1, is before you've added any base at all. So you just have your flask with your acid in there, and you need to calculate the concentration, you need to know the concentration of the hydrogen ion, and then you can find the pH just using the simple pH equation. The second position is after we've added some base, but not as much base as we had acid. So at this point, we need to figure out, okay, the acid's going to react with the base, so let's say we have something like hydrochloric acid, and we're going to add sodium hydroxide to that. Well, this is going to react with each other and neutralize, but at this point we have not added as much of this as we had of this. So therefore there'll be still some of this left over, but this will all be gone. So we need to do a rice table to figure out how much of, so we get rid of all of this, and then how much of this do we have left. And then we can put that into our pH equation and find the pH. Position 3 is called the equivalence point. So this is a little vocabulary term for you. At equivalence point, this equals this. How much of this we have equals how much of that we have. That means our stoichiometry is equal. If stoichiometry is equal, we're talking about moles. So be really, really careful here because you have to have moles rice tables for all of this, not molarity rice tables. At this point, if you have a strong acid and you have a strong base, you're neutral. You have some kind of neutral salt and water. Position 4 means I've overshot and I've added more base than acid. And so then it's the same idea as position 2, only in reverse. Now we're going to do the rice table to eliminate the acid, figure out how much base we have left, and that will be our concentration of hydroxide, which means we can't find the pH, we have to find the POH. And so the POH is the negative log of the hydroxide, and then we subtract the 14 to find pH. So this is how to figure out what's the pH at any point on the titration curve. So let's do an example. All right, let's say that we are starting with 50 milliliters of a 0.1 molar solution of hydrochloric acid. And we're going to add 0.1 molar sodium hydroxide. First, we're going to add 49 milliliters of our sodium hydroxide. Well, again, I said that these rice tables have to be in moles. So we need to figure out how many moles of each of these things we have. So first, the hydrochloric acid. Again, molarity equals moles over liters. So we have our molarity. We need to know how many moles, and we have our liters. Okay, so then that gives us 0.005 moles of hydrochloric acid. For our sodium hydroxide, we have the same concentration. We're trying to find moles, but this time we have 0.49 liters. So this gives us 0.0049 moles. Okay, so if we do our rice table, we love our rice table. We don't care about the chlorine, and we don't care about the sodium. And water doesn't show up in the rice table anyway. So then we are putting in 0.005 moles of hydrogen, 0.0049. We subtract whatever was the smallest. And so then we have left and none of this. Okay? But again, these are moles. It's a moles rice table. So if we want to find pH, then we have to figure out what's our molarity again. So now we have 0.0001 moles of hydrogen. And now we have 50 milliliters plus 49 milliliters, so that's 99 milliliters. And so our concentration is for our hydrogen, then we just take the negative log of this, and that gives us a pH of 3. All right? Now try this yourself. Try adding 51 milliliters of the sodium hydroxide and seeing if you can figure out what the pH is, and we'll check our answer together in class. All right, so that is strong acid, strong base titration. Now let's say that we're doing a weak acid titration. So now I'm going to write purple. Everything in purple is going to be for weak acid. We are still going to use a strong base. You never do weak and weak. That would take forever. Okay, so we're doing a weak acid, strong base. What's going to be different? Well, for one thing, the pH is going to start off higher. But it's going to end in the same place because we're still using a strong base. Now we still have positions 1, 2, 3, and 4. However, calculating the pH is going to be different because it's now a weak acid. So if we are in position 1, again, that's before any of the base has been added, but we can't use this to calculate the pH because now we have some kind of weak acid, so let's say hydrofluoric acid, and it's an equilibrium. So now, in order to calculate the pH, we're going to have to use the Ka. And I'll just put X here because we don't really care what the anion is. So we have to know what the Ka is and know what our initial concentration is so that we can solve for our hydrogen ion and then put it in here. So that's position 1. Position 2, we've added some base, but not as many moles as the acid. Again, we need to use a rice table to eliminate the base to figure out what our hydrogen ion concentration is going to be. At position 3, again, we're at the equivalence point. The number of moles of our acid is going to equal the number of moles of our base. However, our pH is not neutral this time because it's a weak acid, strong base. The pH is going to be basic. So if it's neutral, we know what the pH number is 7.00. But if it's basic, we're going to have to figure out what that pH is. So again, we're going to have to do a rice table. I'm sorry, we don't have to do a rice table. At this point, we have to figure out how many moles of the acid we've had, and that's how many moles of base we have, and then take our moles of base, divided by our total volume, and that will give us our hydroxide ion concentration. And then we can take that, find the pOH, and then find the pH from there. Position 4, we've overwhelmed our weak acid, and now all we have left is a strong base. And so again, we're going to do a rice table to eliminate the acid and figure out how much base we have left, and then we can put in for pOH and the pH at the end. So that part's the same, because we've just gotten into a strong base. But the only difference is that we're going to have to do rice tables, and we're going to have to use Ka, which is Ka again here. And then the Ka will give us our hydrogen ion concentration, which we can then put into the pH equation. And we will do a practice problem in class of a weak acid titration, because it's a little more complicated than what we just did for our strong acid, strong base. Thank you.